Okay. Good morning to everyone. The appointed chair could not connect apparently, so I will be your chair. My name is Lorenzo Calibbi. Welcome everyone to this morning morning plenary session of our SUSY conference. This morning we will be discussing mainly about axioms. I remind the speakers they have 25 minutes, including discussion, so please try to keep 2-3 minutes at the end of your talk for questions and discussion. So the first speaker is Professor Pierre Sikivi, who is going to talk about axion dark matter, right? So yes, thanks for sharing your slides, and please start whenever you are ready.
Thank you. So thank you very much for the opportunity to talk at the SUSY conference. I will not say anything about symmetry except that I think it is emotionally correct. My topic is actually axion dark matter. What I mainly want to do is to make distinctions between the way axions behave and WIMPs behave at some fundamental level. This work is done in collaboration with Charlie Yang, who was a student at the University of Florida, and I have a picture of him there when he was a student. I think he looks more professorial now. Also, Erken, Haywood Tam, and Yang, and Nilanjan Banik, and Elisa Todorello. So we asked today, what is the dark matter? Maybe it would be wise to go back a few centuries after Newton and others had established the laws of classical mechanics, and they had this big question at the time: what is the nature of light? And this has a very interesting history, I think, which runs deep in physics. Newton thought it was a stream of particles, and Huygens thought it was a wave. And then Young did experiments and showed interference patterns that showed the light is a wave. But that is not the end of the story, because at the end of the 19th century, Planck showed that no, in fact, light is a stream of photons. So there's a particle-wave duality. And actually, quantum field theory gives a satisfactory description of this duality. So in quantum field theory, you have a set of oscillators. Each oscillator corresponds to a particular wave of a field, and the oscillations are quantized. So the energy is a sum of energies omega A dagger A for quantum oscillators. And of course, there are also interactions, A dagger A, which are not important for the time being. So you all know that we construct these quantum fields as sums of waves and the associated annihilation operators and Hermitian conjugate. And we know many such fields. These are the fields of the standard model. There's the electron, the muon, and associated neutrinos. They are the quark fields. They are the gauge fields. And then there's the Higgs boson. We also know that none of these particles are adequate as a dark matter, because actually most of them are unstable. The best candidates are the neutrinos, but the neutrinos move too fast together in galactic halos, so they are called hot dark matter, and they are inadequate. The electron, of course, is too visible. The photon is too visible. The other attractive candidate is actually baryonic dark matter, which is neutral particles made out of quarks and gluons. But this is also unacceptable because we know from nuclear synthesis that the fraction of baryons, the density in baryons today is not large enough to account for the dark matter. And we also know this from the CMBR and also from searches for baryonic dark matter that did not show up anything. Now, we want to ask, I think, what is the dark matter? We think it's a quantum field. What will be its manifestations? And I want to point out, I think it's correct to say that most of us are heavily prejudiced in favor of particle dark matter, because everything that we encounter most of the time is a particle. If you look at all these particles, actually I call them particles, they're quantum fields. There's almost never you see them manifest themselves as a wave. The one exception is the photon field. Actually, it has high energy gamma rays behave like particles, but the microwave photons that drive, say, your cell phone or your radio, they are really waves. You think of them as many photons in the same state. Now, I think I like this picture here, which comes next. This is interference patterns between Bose-Einstein condensates that were made in Ketterle's lab, and the two condensates overlap, and when they overlap, you see an interference pattern. And this is a manifestation, I think is the only one I'm aware of, where atoms actually manifest their wave nature, as is expected. So the Hilbert space of quantum field theory, as you know, is a sum over states in Fock space, and Fock space states are given by giving how many quanta you put in each wave. So there's wave number one and one quanta, wave number two, and so forth. Okay, I'm saying things that are very elementary. So how do you go to quantum mechanics? To go to quantum mechanics, you put one quantum in one wave and have no other quanta. And you work this through, the quantum field theory will produce the Schrödinger equation for this, for the mode here that this one quantum is in, if it is a non-relativistic particle. If it is a relativistic particle like a photon, then you'll have this wave equation. Now you all know this, I want to emphasize that this is just as much, you think of this as quantum mechanics, but this is just as much quantum mechanics, even though you derive it from Maxwell's equation when you apply it to a single quantum. And A would have a probabilistic interpretation. Now, how about the classical limit? There's actually two classical limits of QFT, and they correspond to the particle limit and the wave limit. In the classical particle limit, you go first from QFT to quantum mechanics, and then to classical mechanics by taking h bar equals to 0, keeping the energy and the momentum of a particle fixed so that the frequency and the wave vector become very large, and you can no longer see the wave nature. To take the classical field limit, you also take h bar equals to 0, keeping the energy and momentum fixed, but now you keep the frequency and the wavelength fixed, but you occupy the state by many quanta. So now the occupation number goes to infinity. So this description is really mathematical. Of course, h bar doesn't go to 0. H bar has a definite value. So in a way, it's more physical to keep h bar fixed and think about it this way. The particle description is when the uncertainty in position is much less than the interparticle distance. Then by Heisenberg uncertainty principle, this constrains, if you follow this through, the phase space density in units of h to the minus 3 to be very much less than 1. So phase space is actually a very useful tool for analyzing dark matter, because dark matter is collisionless. So here I have a two-dimensional phase space, and I have a x and a momentum and two particles in it. Of course, I imagine there's a very large number of particles, but it takes too much time to draw infinite, very large number of particles. So the particles, this is the interparticle distance, and this is their momentum dispersion. The phase space density is two particles in this volume. The phase space density has to be very low in units of h to the minus 3. for the particle description to be valid. The wave description, on the other hand, is valid when the phase space density is very large. So now all these wave functions overlap, and you have the particles in some region of phase space with very many particles with overlapping wave functions. So I drew this in blue. Okay, and so you can then show that N is the quantum degeneracy. N is the number of particles that are in the single state, or is the occupation of those states that are highly occupied. And of course, you can only do this for bosons. Okay, just a quick, let's talk about WIMPs and let's talk about axions. Again, I'm not saying much here. I think that you don't already know. WIMPs are produced in the early universe by freeze-out. They annihilate till they become so dilute they don't find each other anymore. And this typically happens at a temperature which is 1/20th the WIMP mass. They are still in kinetic equilibrium with neutrinos because they interact with them, but then the neutrinos become dilute and they stop interacting with them. They decouple. This happens at a temperature of order MeV. From this, we can deduce, first of all, the number density of WIMPs. It's of order less actually than 1 per meter cubed, because we know the energy density of dark matter, and we know the mass of the WIMP. But also, we can calculate the momentum dispersion. It corresponds today to the velocity dispersion of the WIMPs to be of order 10 to the minus 12 in units of the speed of light. And we can calculate the size of a WIMP packet, wave packet, and it is of order micrometer, actually 15 micrometer. So the WIMPs are extremely degenerate. Their degeneracy is of order 10 to the minus 13. Now, in contrast, axions have masses of order 10 to the minus 5 eV. They are produced by various mechanisms during the QCD phase transition, which have been described on many times. So let me not describe them once more. But in any case, the momentum dispersion of the axions during the QCD phase transition is given by the horizon. That is to say, the age of the universe then, which is of order 10 to the minus 7 seconds, when the temperature is of order 1 GeV. So this then tells me how many axions there are, and it's of order 10 to the 8 per centimeter cubed. But they are very highly delocalized. If I take the momentum dispersion today, and it corresponds to a velocity dispersion of order 10 to the minus 17, they are quite a bit colder than WIMPs in this regard. They will have a lower velocity dispersion. And they are very highly delocalized because the inverse of the momentum dispersion is of order a light year. Actually, it's for the 1/50th of a parsec. And the degeneracy is truly enormous. It's of order 10 to the 61. Remember that to make a Bose-Einstein condensate, people try to achieve a degeneracy of 1. This is 10 to the 61. So axion dark matter is truly a very degenerate Bose gas. And now I want to ask, does it behave the same as WIMPs? Remember, for a long time, one could not tell the difference between a particle description of light and a wave description. So in a way, we have a similar question today. So let me consider a glob, which I don't know what it is. It's dark matter. I don't know what it is. I'm supposing it could be WIMPs or it could be axions, and I'm sitting at some point x0. And the only thing I can know about this glob, this dark matter, is its gravitational field, because it does not interact in any other way. And I'll take the glob to be of order a light year. Now, if I imagine that this glob is made of WIMPs, I can calculate this of order 10 to the 47 WIMPs, but also you can put them with a precision of order their delta X, which was a micrometer or 15 micrometer. So there's an enormous number of ways I can construct this glob. The number of, there's 10 to the 13 states per WIMP, and there's 10 to the 47 WIMPs. And so if you look at this glob, the field is very much, the gravitational field is very much like that of this dark matter. But if I think this glob is made of axions, and I took the wavelength of the axions, the inverse, not the wavelength, the inverse of the momentum dispersion to be of order the size of the globe, a little bit less, then there's actually relatively few ways in which I can construct the globe. I calculated 10 to the 62 axions, but there's 10 to 61 axions per state. So there are only 30 states that can be occupied. And for example, I cannot make these sharp boundaries. That's impossible. So this is different, actually. Let me emphasize the role of this inverse of the momentum dispersion, which I call the correlation length. If the wave function is psi and the Fourier transform is psi of p, and the Fourier transform is localized in momentum at p naught with some dispersion, then you can show quite easily that the density must be approximately constant on a scale 1 upon delta p, because both p and p prime are within this delta p. P naught is irrelevant, and so this does not scale with x unless you change by x more than 1 upon delta p. So this L, 1 upon delta p, is really the correlation length. And gravitational fields, gravitation is long range. So necessarily, if the density does not change over distance L, then the field associated must be of order 4 pi g rho L. I call that delta G. This must be the typical value when you construct this, regardless of the average value. So let me give the example of a homogeneous universe. In a homogeneous universe, there is no acceleration, say at one point, right? In the WIMP case. But in the WIMP case, the gravitational field is truly zero. In the axion case, the average field is zero, but the fluctuation cannot be zero. It has to be of order 4 pi g rho L. So there are large gravitational fields and therefore large gravitational forces. So here's the momentum distribution of the axions, and there are forces, gravitational forces pushing them back and forth due to the fact of these large gravitational fields. And you can ask, how quickly does the momentum distribution completely get reorganized? Well, since the gravitational field is delta G and the mass is m, this is the relaxation time, the time scale over which by self-interactions, gravitational self-interactions, the axion fluid will change its distribution completely. This turns out to be today of order 24 seconds. So it happens immediately if the conditions that I described were true. Or in other words, it must have happened a long time in the past. When it happens, you must form a Bose-Einstein condensate because all conditions for Bose-Einstein condensation are satisfied. You have identical particles, their number is conserved, they're highly degenerate, and they are thermalized. So with Charlie Yang, 12 years ago, we calculated when does this occur in the early universe by comparing the relaxation rate, which I just described, with the Hubble rate. We found that at QCD time, the relaxation is not fast compared to the Hubble rate, so it does not occur. But this ratio of the relaxation rate to the Hubble rate increases with time because the Hubble rate goes down like 1 scale factor to the -2, whereas the relaxation rate goes down like scale factor to the -1. Okay, so we find at a temperature of 400 eV, you must form this Bose-Einstein condensate. So my question was at the start, how does axion dark matter differ from WIMP dark matter? Well, if you have WIMP dark matter, you can describe it by the continuity equation and the Euler equation. It's a fluid that satisfies the continuity equation and an Euler equation with the force being the gravitational force due to all the WIMPs. So it's the gradient of the Newtonian potential. In the axions, now, here's an important assumption. If you put all the axions in a single state, and this is the wave function of that state, and they remain in that state, then also you have a continuity equation. The density is simply psi modulus squared, and the velocity is given in terms of the phase of the wave function by this gradient here. But the Euler equation has the force due to the gravitational field. There is an extra term, which is sometimes called quantum pressure. I think it's a little unfortunate as a name. I think it would be better be called wave pressure. What does this describe? Let's suppose we turn off gravity and we make a pile of WIMPs. Well, the WIMPs will just sit there, but the pile of axions will disperse because of the wave nature of the axion field. And that's actually described by this gradient of Q. So if you balance the attractive nature of the gravitational field against the dispersive nature of this wave pressure, you find there is a Jeans length. And it is relatively short for axion masses of order 10 to the minus 5 eV. But if you make the mass very small, of order 10 to the minus 20 eV or so, then this becomes of order 100 parsec or 4. So. This Jeans length, I think, was originally pointed out by Klopov, Malumet, and Zeldovich a long time ago. But I want to draw another distinction, and I'm more or less on time. If you observe the fluid, the axion fluid, on time scales larger than this thermal relaxation time, the axions thermalize. When they thermalize, they do not stay all in the same state. That's impossible, because if they did, they would obey classical field equations. But we know that thermalization in classical field theory has a different result from thermalization in the quantum field theory. In the classical field theory, you produce this so-called Rayleigh catastrophe, the ultraviolet catastrophe that Rayleigh pointed out in electrodynamics. Whereas in the quantum theory, you move towards a Bose-Einstein distribution. So it must be necessarily true that quantum effects are important. And that must be because must mean that the particles do not stay in the same state, but move between states. That means further that you can produce vorticity in the axion case. Because when you can move between states, you can move between states of different vorticity. For example, you can go from state L1 and L2, angular momentum L1 and L2, L3 plus L4, conserving angular momentum, but the vorticity of each state is different. In the case of WIMPs, you don't produce vorticity because this is a gradient. And if you keep all the axions in the same state, again, you don't produce vorticity because this is a sum of two gradients. So there is actually the basis of distinguishing on the basis of vorticity generated axions from WIMPs. And you should expect in the axion case vorticity to be generated because the lowest energy state for given total angular momentum is a state of rigid rotation in the angular variables. So this is actually my main message. And thank you.
Thank you very much, especially for being so perfectly on time and a nice talk. So please, questions. If anyone has got any question, just please open your microphone.
Can I ask a question?
Please.
Sure.
So thank you. It was a very interesting talk. You know, when we're talking about correlation lengths and thermalization, obviously, to me, it sounds somewhat reminiscent of like the classical theory of phase transitions. I don't know if these results can be interpreted in that context.
Yes. Let me go back. Oops. I'm sorry. I'm no longer screen sharing. Okay. So you can describe actually Bose-Einstein condensation in classical field theory. Maybe this is what you're alluding to. Is that right?
Well,
By
yeah,
introducing the cutoff. Is that right?
yes. Yeah. That's partially what I'm getting at. I suppose what I'm interested to know is, for example, in the context of this dark matter, what would be the relevant order parameter that we would pay attention to?
Well, the order parameter is the correlation length. So the correlation length grows when you make a Bose-Einstein condensate. Bose-Einstein condensation can be produced in the classical field theory by introducing a cutoff, but that cutoff is purely fictitious. And in the case of axions, you would have to put it at extremely low momentum to produce the required effect. So also, this is not the true theory, and it does not have the same implications, even though it has Bose-Einstein condensation. Because when you introduce the cutoff, you will not be able to produce vorticity. The cutoff theory is no more able to produce vorticity than the theory without cutoff, whereas the quantum theory will be able to produce vorticity. This is Nick, right?
Mm-hmm. Yeah. This is me.
Good.
Okay, thank you.
Thank you.
Any other question? If not, so thanks to our speaker again. And yeah, please stop sharing. Yeah, perfect. And we can move on. So next speaker is Professor Ki-Won Choi, who's going also to talk about precision axion physics with running couplings. Please.
Okay, thank you very much. Many thanks to the organizers for the kind invitation. Today, I'm going to talk about the precision action physics with running action couplings that include the radiative corrections. My talk is based on these two works done with my collaborators, Sang-Hee Im and Chang-Sap Sin, and Yan-Sak Song and Hee-Jung Kim. Oops. Okay, this is the outline. So after brief introduction, I will discuss the three types of action models with different pattern of low energy couplings, and then examine the possibility to distinguish those different type of actions with experimentally measurable action couplings. All right, as you know, the axions or action-like particles are light pseudoscalar bosons, which have been postulated to solve various issues in particle physics and cosmology. That includes the, of course, the strong CP problem and dark matter, the issue of dark matter that has been discussed by the previous speaker, Pierre Skibi, and even for the early universe inflations. One of the key features of actions is that it has a finite field range parameterized by a scale parameter called the action decay constant. As a consequence, the all action couplings are naturally inversely proportional to the this action decay constant. Another important feature of actions is that the interactions of actions are constrained by an approximate nonlinear Pechakian symmetry, which includes the constant shift of action field in low energy vector theory. Well, to avoid the confusion, let me make terminology more clear. In my talk, I'll use the term actions or ALF for generic pseudo-Nambu-Goldstone bosons associated with the general form of U1 Pechakian symmetry, and the term for QCD action, the term QCD action for a more specific type of actions with UN patch-checking symmetry, which is broken dominantly by the QCD anomaly, so that solves the strong speed problems. Okay, anyway, the actions generically can be classified by several different ways. One way to classify action is by the origin of the field variables. In that case, there can be two possibilities. The one which I will call the field theoretic actions, which originate from the phase of some complex scalar field, and another type of actions, which I will call the string theoretic actions, that correspond to the zero mode of some higher dimensional antisymmetric tensor gauge field. Of course, in theory, it's with extra dimensions. One key difference between these two types of actions is that for field theoretic actions, I mean, you have UV completion of your theory with linearly realized UN patch-checking symmetry. That means that corresponds to the the limit that the action decays constant is vanishing, while the string theoretic actions do not have such a limit. That actually made the some important difference for instance, the cosmology of the actions. In any case, there is another way to classify the actions, for instance, by the measurable low energy couplings. For this, let me consider a generic action coupling to the photon and gluons and light quarks and electrons at scales about 1 GeV, just above the QCD scale. Then generically in this prescription, the action coupling to photon and gluons described by the quantized rational numbers, the gamma and CG in this description. The action coupling, derivative coupling of actions to the axial vector currents of the light quarks electrons, they are parameterized by real valued continuous parameter C psi. And for my next discussion, let me decompose this C psi into two pieces, the tree-level values and the radial corrections. Then, as we will see, there are three different possibilities. The first is the so-called field theoretic DFSP type actions, in which this tree-level value of the action coupling to light quarks and electron has order 1 value in this prescription. And the KS-bridge type actions with vanishing tree-level coupling to the light quarks and electrons. That is in the limit that you include only the renormalized interactions. But of course, if you include the Planck scale suppressed higher dimensional operators, there can be some small contribution to this coefficient that can be safely ignored in my discussion. The third possibility is the string theoretic actions, for which this tree-level coupling of the action to the light quarks electron is order of the gut scale fine search constant divided by 2 pi. Well, once you can identify, I mean, you determine the action couplings at scales about 1 GeV, just above the hadronic scale, then you can easily, it's straightforward to express the real experimental measurable low energy action couplings at scales below 1 GeV and at scales well below the QCD scale. For instance, the action coupling to photon, action coupling to nucleons and electrons are determined in terms of the higher scale parameters, C gamma and CG, and for instance, the action coupling to the light quarks renormalized at 2 GeV, for instance. So anyway, if you, in regard to the experimental verification of actions, there are three interesting examples of well-motivated light actions. For instance, in this action parameter space spanned by the action mass and measurable action couplings. Of course, the best motivated and the most interesting one is the QHD action represented by this light blue, shaded band. Which shows that for QHD actions, both the action coupling and action mass, they are both proportional to the inverse of the action decay constant. Another interesting possibility is the so ultralight action like particles. For given action couplings much lighter than the QHD action, for instance, that would be the case, for instance, if ultralight, this action does not couple to gluons, but still couples to photons. The third interesting example is the ALP dark matter produced by the misalignment, for which the ALP coupling is proportional to the one force power of the action mass for given value of ALP dark matter density. So we have these three different interesting examples of the parameter regions in the action parameter space. So this plot shows the current status and future prospect for the for the action photon coupling as a function of the action mass. This color shaded regions are already excluded by the either astrophysical observations or the laboratory experiment, and all of these dotted curves represent the sensitivity limit of the future planned experiment. This is the famous the resonant cavity experiment proposed first by Pierre, and there are some new ideas to explore this the bulk region of this ultra alpha parameter space using the optical link cavity or the SNF cavity or this abracadabra experiment. So in any case, you can see that the majority part of this ultralight alpha parameter space can be explored by the future experiment. Of course, also the large portion of the QCD action region also can be explored. So that's very exciting possibilities. On the other hand, the status and future prospect for the action nucleon coupling and the action electron coupling is poor. I mean, in particular, the prospect for the action coupling to electron is the poorest. But still, I would like to stress that once an action is discovered by any means, whatever it means, whatever it is. So if you could fix the action mass, then I think it will be much easier. That this information is so important. Information of the mass is so important that it will be much easier to experimentally measure the action couplings, including the action nucleon coupling and action electron coupling. That may make it possible to determine all of these four couplings, four action couplings to the photon, neutron, proton, electron together in some future. That's the I think kind of situation that you can imagine. Anyway, let me come back to the theoretical calculation of the action couplings. So for the case of the couplings of field actions, they are essentially determined by the quantized Pecheckian charge of the linearly realized Pecheckian symmetry. As I mentioned, the key feature of the field action is that it has a UV limit with the linearly realized Pecheckian symmetry. So, for instance, unless you consider really crazy models, these quantized Pecheckian charges are usually over the unity, or for some fields precisely vanishing. So for the field actions, the quantized couplings, the photon and the gluons are essentially determined by these Pecheckian anomalies with the electromagnetic ion gauge symmetry and the QCD SUSY color symmetry. Also, the three-level couplings, the light quarks and electron of these field actions, again determined by the Pecheckian charge of the relevant light quarks and electrons, and also the Pecheckian charge of Higgs fields and their vacuum values, represented by these dots. In any case, so because they are essentially determined by the quantized Pecheckian charges, there can be essentially two possibilities. One is the DFSP type, for which the standard model fields are PQ charged. That means that the action coupling, the three-level action coupling to the light quarks electron in my prescription is order 1. But for the KS bridge type, in KS type action models, the standard model fields are PQ natural. That means that unless you ignore this tiny contribution from the Planck scale suppressed interactions, the three-level coupling to the light quark electrons are precisely vanishing. Well, but the coupling of string theoretic actions are determined by a completely different way. In any case, for each string theoretic action, one important feature of the string theoretic action is that for each string theoretic action, there exists a modulus partner which forms an N=1 chiral superfield together with the action. So that, for instance, if you use the angular action field with 2π periodicity, then its modulus partner actually can be the vacuum value of its modulus partner can be identified as in this normalization of actions, identified as the Euclidean action of the brane instantons, which is the low energy consequence of the brane, which couples to the underlying p-form gauge field. Typically, this modulus partner is either proportional to the volume of the internal space or some power of the inverse of string couplings. At any rate, so then the size of this modulus vacuum value is quite crucial for the strength of the action coupling to the light quarks and electrons. Let me discuss some constraint on this modular vacuum value. One constraint comes from the so-called action Euclid conjecture, which provides that the upper bound on the Euclidean action of these corresponding brane instantons. So it provides the upper bound given by this on the modular vacuum values. Also, because we are mainly interested in the light action, such as the QCD action or ultralight ALP, action like particles. On the other hand, there can be always action, again, according to the action Euclid conjecture, there is action potential induced by the brane instantons, which can be parameterized by this way, first suppressed by the exponential of the instanton action and some model-dependent scale parameter lambda, which is typically determined by the gravitational mass. In any case, we wish that this brane instant-induced extra action potential does not spoil this elegant Pechakin solution of the strong CP problem. That means that for the QCD action, this extra action potential induced by brane instanton should be suppressed enough. I mean, numerically less than about 10⁻10 times of the the action size of the actions action potential induced by the QCD instanton. That provides the lower bound on this modulus vacuum value. Similarly, for ultralight ALP, we are more interested in the very light action like particle, so that certainly this brane instant action potential should be bounded by this, where the MA is the total ALP mass. Again, this provides the lower bound on this modulus vacuum value given by this. Numerically, for any reasonable range of the gravitational mass, numerically that this provides this suggests that the modulus vacuum value should be bigger than about 100. There is another upper bound on the modulus vacuum value from that if your action couples to either photon or gluons, then actually the gut scale time structure constant, its inverse actually involve the contribution from given by this modulus vacuum value. As a consequence, if this modulus vacuum value has a too large value, that will give the standard model gauge coupling too small. That provides the upper bound on modulus vacuum value. Putting all this together, I mean, these two upper bound and two lower bound, some kind of lower bound, that strongly suggests essentially for light actions that you are mainly interested in, like QCD action, ultralight ALP, the modulus vacuum value should be order of the 2 pi times 1 over alpha gat. So this is very crucial feature of the string theoretic actions, and that applies again only for the light actions that you are mainly interested in. Anyway, basically the couplings of string theoretic actions, again in the unity of the 1 over the FA, are determined by how the standard model couplings or the metafield calorimetry and modular Keller potential depends on this modulus field tau. So that that tells that suggests that at least in the limit that the modulus vacuum value is significantly larger than other unity, the 3-level coupling of the string theoretic action to the light quark and electron, more generically the matter fields and Higgs fields, should be order of 1 over tau. So that suggests that for generically string theoretic actions, the 3-level coupling of the 3-level action coupling to light quark and electron is given by this. Well, although here I only provide some very naive order of magnitude estimations based on this scaling behavior, actually you can explicitly calculate the coupling of actions for various examples of string theory actions and make sure that this is actually the correct estimations. Anyway, so putting all this together, there can be basically 3 different type of actions in view of the pattern of the Lagrange couplings. One is the DFSG type actions, for which the 3-level coupling of action to the light quark and electron, and also the coupling to the photon and gluons, they are comparable to each other. KSVG type, basically vanishing 3-level coupling to the light quark and electrons, and string-theoretic actions, for which the three-level coupling of the light quark electron is about the alpha got over 2 pi times the coupling to the coupling to the photon or gluons. In these prescriptions. So the next question is that would it be possible to distinguish these three types of actions by experimenting measurable election couplings, couplings to the photon and the nucleon and electrons at scales well below the Richter scale? For these questions, one notable point is that both KS-VG type action and string-theoretic actions, they have this coupling ratio numerically quite small. That means that we need to include relative corrections to the matter coupling to light quark electrons if we wish to examine if the KS-VG type and string-theoretic actions can be distinguished by the measurable low-energy couplings to the nucleons and electrons and photons. Of course, basically the pattern is determined by the ratios among these measured couplings. Well, before moving to the discussion of the relative corrections, let me briefly mention if there exists any range of the action decay constant for string-theoretic actions theoretically favored. Well, for relatively simple compactifications, which does not involve a big hierarchy between the string scale and the 4D Planck scale, then actually it turns out that the decay constant of the string-theoretic actions is actually given by this, Planck scale times the alpha got over 2 pi, numerically about 10 to the 16 to 10 to the 17 GeV. But as usual, the string theory is so much flexible so that can accommodate usually any kind of possibility, so that eventually, if you consider the more involved string compactifications, for instance, compactification with large volumes, large compacting volume, or involving a large warp factor, which would generate a big hierarchy between the string scale and the 4D Planck scale. In those situations, the decay constant of the string-theoretic actions actually, can have any values, for instance, between this lower bound from astrophysics and this kind of upper bound from the Euclid conjecture. So that in that sense, even for string-theoretic actions, we can treat FAs essentially of free parameters, which can have any value in this wide range. All right, now let me move to the relative correction to action couplings described by the RG evolution. For this, we can start from the action couplings defined at high scale around the action decay constant. And then basically there can be two kinds of relative corrections. One is the Yuga couple induced one loop correction, and the gauge couple induced two loop corrections. So I'm not going to discuss because of time limitation, I'm not going to discuss any detail of these corrections. This part. But in any case, you can have two kinds of relative corrections: Yuga coupling induced and gauge coupling induced. And putting all these corrections to the low energy measurable action couplings to the photon and proton and nucleon and electrons, and consider their ratios. For instance, three ratios. The proton to photon coupling ratio, neutron to photon coupling ratio, and electron to photon coupling ratio. That includes the corrections. So this plot actually summarized the result for some specific examples, which I think represent the characteristic features of for many different type of models. For instance, for the case of QCD actions, which has the non-vanishing coupling to the gluons, we see that all three types of QCD actions, DFSD type and string-theoretic actions and KS-VG type, they all have a similar value of proton to photon coupling ratio. This is mainly because of the contribution from the action coupling to gluons, which all different type of actions share for the QCD actions. Yet they have a clearly distinguished pattern for the other two coupling ratio, for the neutron to photon coupling ratio and electron to photon coupling ratio, as represented by these two plots. This green line represents the DFSG type models, and this black line is for the KSVG type models. But KSVG type model involve another parameter, the mass of the exotic heavy quarks. So that I'm using for this plot, I'm assuming that this heavy quark Q has the mass in this range. Finally, this red line represents the string-theoretic actions in so-called the large volume scenario, which allows the action scale can be anywhere in this range. So for actions, the neutron to photon coupling ratio shows this pattern, and electron to photon coupling ratio shows this pattern. So that with these coupling ratios, in principle, you can distinguish the different type of actions with these experimentally measured couplings. For the case of ultraviolet ARP, what I mean by ultraviolet ARP means that, okay, it doesn't have the coupling to gluons, but has the non-vanishing coupling to photon through the coupling to the electric gauge bosons. For this case, the situation is somewhat better. Different type of ARPs, KSVG type, DFSG type, and string-theoretic type, they all have clearly distinct pattern for all three coupling ratios. The proton to photon ratio and neutron to photon ratio and electron to photon ratio, as shown in this, as summarized in this plot. Well, let me finally mention the kind of bonus from our study. We found that through this analysis of radiated correction to the action couplings, we found the coupling of KSVG type QC action to the electron is actually dominated by the higher loop diagrams that has been ignored in the previous studies. So usually people have considered, when people consider the calculated action coupled electron for KSVG type QC actions, people consider the radiated correction mediated by electric gauge bosons, which is represented by this term in this equation. Of course, there is also a model independent contribution by the action pion mixing. But we found that numerically, this higher loop contribution involving top quarks and Higgs field and G bosons, they give the most dominant, the dominant contribution to the action electron coupling for the KSVG type QC actions. Numerically, we see that, okay, this represents the action electron coupling mediated by the ion hypercharge gauge boson, mediated by the SU2 gauge bosons and action pion mixings. And finally, this is the contribution for this figure. So that you see that the higher loop contribution, which was not considered before, gives the dominant contributions. All right, let me conclude. Basically, there can be three types of action theoretically with different patterns of low energy couplings: DFSG type, KSVG type, and string-theoretic actions. Among these, both KSVG type actions and string-theoretic actions have suppressed couplings to the light quarks and electron. Therefore, we need the precision analysis, including the radiated corrections, if we wish to distinguish between KSVG type and string-theoretic actions by experimental measurable ratios of these couplings. For QC actions, we found that the electron to photon coupling ratio of KSVG type and string-theoretic actions differ by about an order of magnitude, while the nucleon to photon coupling ratio are similar to each other. For ultralight ARPs, which does not have the coupling to gluons, again, that's a very interesting possibility. In view of the experimental exploration of the action parameter space, different type of ARPs have clearly distinct pattern for all three coupling ratios. The proton to photon and the neutron to photon and electron to photon coupling ratios. Finally, we found that the coupling of KSVG type QC axiom to the electron is dominated by a higher loop contribution involving the top quarks and Higgs bosons, which was ignored in the previous studies. Okay, this is all. Thank you very much for your attention.
Thank you for the very clear talk. So the session is open to questions, please. Anyone? Just open your microphone. Okay, while people are thinking, maybe I have one myself. So if I understood your plot correctly, you are showing that, well, for instance, for KSVZ, it's unavoidable to induce, due to this radiative correction, a coupling to electron, which is about, 10 to the minus 2, 10 to the minus 3 times the coupling to photon. Is that correct?
But okay, this I'm not sure about that number, because you see, my case, usually we define the okay, let me move this this parameterization of the experimentally measurable action couplings, right? Action coupling to photons, action coupling electrons, right? Defined this way. So then this is my result for KSV's actions. So here I did not directly provide the ratio between the action coupling electron and action coupling photons, but in any case, somehow I'm sorry, I just show I compare this new contribution.
Right.
The previous the result of the previous analysis.
Right.
I'm not sure. I mean let's see, 10 to the minus roughly 10 to the minus 3 times the okay. In any case, this CG is order 1, so about 10 to the minus 3 times of CG times electron mass divided by F of A. And on the other hand, the photon coupling is always have this, by definition, you have this,
right,
factors, right? So that numerically maybe less 10 to the minus 2 or 10 to the minus 1 difference.
Yes, yeah. So you have
also
anything?
It involves the action mass, so that yeah.
True. So okay, yeah. Since it's important for model discrimination, as you have shown, so you have any idea about measuring at a laboratory experiment the electron coupling?
Well, that's, I think, as I mentioned this, that the possibility to measure the action coupling electron is the poorest. I mean, of course, mainly because the electron is much lighter than the nucleons. But as I mentioned, I mean, at some point, if we discover the action and determine its mass, I think the situation hopefully may be a lot better, so that maybe we might able to even measure, or at least provide the meaningful upper bound,
Yes.
the action coupling to the electron also. Yes.
Okay, thanks. So I
long time,
see. Yes.
Yes.
I see someone raised their hand. Keisho Idaka, please.
Yeah. I have a question. Can action couple to heavy lepton and the heavy quark and the massive gauge boson?
Absolutely,
For
yes.
example, mu pair Higgs, for example, action muon pair coupling and action Z pair coupling, and also action charm pair coupling, they are possible?
The action generically can couple the any particle in the standard model. But here, I just focus on the action coupling to the light quark and electron and photons and gluons, because I'm more or less interested in the very light actions, which can be discovered by through the action coupling to nucleons and electron or photons. So of course, you're right that this generically action can couple to whatever particle, heavy leptons, heavy quarks, and electric gauge G bosons and W bosons. Absolutely possible. But in this low energy limit that I'm focusing on, those couplings are irrelevant. So that's why I focus on the coupling to the electron and the nucleons and photons.
And but yeah, okay, I understand. So experimentally, for the collider experiment or beam dump experiment, the action will be produced, and then action could decay into mu pair, and such event could be detected in the such experiment.
Yeah, of course. Yeah, but you know, typically those kind of experiment, I mean, laboratory or accelerated experiment to search for the actual particles, actually probing these regions. I mean, the heavier actions.
Heavier actions.
Heavier action with much stronger coupling. I mean, for the action coupling, you know, which is weak as much as this region. I mean, you don't never see the signals in the collider experiment. So that I would say that the experiment that you are mentioning is basically probing this range. I mean, still
right hand side, outside, okay, right hand side. Okay.
Yes.
Okay. So different story.
Absolutely different regions. Yeah, different
regions. But both regions are accessible by experiment.
That's what we hope. Yes.
Yeah. Okay. I understand. Thank you.
Okay, thank you very much. I don't see other questions.
Okay, I have a question.
Okay, please.
Yeah. Okay, I wonder if the coupling of cathode with loop coefficient can be comparable to that of the string theoretical action. Okay. I wonder if the KFC action coupling the wave loops can be comparable to that of the string theoretical action.
It eventually turns out that the actually there is some minor model dependence that I didn't talk in my talk, which is in the papers. But anyway, for relatively simple type of action models, it turns out that the radial correction in KS-bridge type action models is significantly smaller than the tree-level value of the string theoretic action couplings. So that's why eventually you see that, for instance, the you see, you know, that for the KS-bridge type models, all couplings, they are induced by radial corrections. But for string theoretic actions, this is for the ALP and this is for the QCD actions. For string theoretic actions, you have this non-zero tree-level value, which is order of the alpha got over 2 pi. It's model dependent, but here I'm using a specific model, which give a definite prediction of that coupling at tree level. And this value includes the both tree-level value and the loop corrections. And for KS-bridge type actions, purely loop corrections. So that shows that essentially purely loop corrections is significantly smaller than the, at least for the action electron coupling, significantly smaller than the tree-level coupling of the string theoretic actions. But of course, that's the kind, you cannot definitely answer that question before you actually do the explicit analysis of these radial corrections. But eventually it turns out that, yes.
Okay, thanks.
Okay, thank you very much again. I think we should move on. So next speaker is Professor Jesse Shelton, who is going to talk about long-lived particles, exploring long-lived particles. Are you there? I saw you connected before. Yeah.
Yes.
So please share your screen.
Yes. There we go.
Thank you. Whenever you are ready.
Very good. All right. All right. Good morning, people in the Eastern Hemisphere. Good evening, people in the Western Hemisphere. It is a great pleasure to be speaking. I am talking about long-lived particles. And for those of you who have not been following this closely, there has been an exciting rapid development in the kinds of long-lived particle searches that are coming out of the LHC. This is really notable because these searches are hard. The detectors are not designed to look for particles that travel a macroscopic distance in the detector before decaying. Of course, they're designed to look for B quarks, but for things that are not part of the standard model and do not have sort of typical standard model properties, detectors were not really designed to look for them. So that is both a great benefit as well as a great drawback when it comes to actually doing these searches. The great drawback is you're asking your detector and your reconstruction algorithms to do things that they're not designed to do. And therefore, all of these analyses need to be thought about from scratch, starting at the trigger and going all the way up through reconstruction, efficiencies, and understanding the backgrounds. The backgrounds are also typically much more challenging than they might be in prompt searches because they tend to come from a combination of unusual detector response and unusual truth level physics, which makes them very hard to predict from first principles. On the other hand, the fact that these searches are looking for objects that are fundamentally unstandard model-like in their detector signature is a profound benefit because it means if you can figure out how to identify these events, they are intrinsically much lower background than most LHC searches. And that is a very powerful advantage because it means the searches can be done relatively inclusively. You don't have to put a lot of detailed model-specific cuts on the search in order to obtain a good signal-to-background ratio, as long as you're able to actually record the event to tape and do the reconstruction in the first place. So these searches are hard compared to standard prompt analyses, which is part of why it's taken until now for so much interesting development in the experimental, in the kind and sophistication of the experimental searches on these signatures to have come out. So now as a theorist, it's very exciting to watch the enormous creativity and talent of the experimental collaborations as they push forward the search for long-lived particles on a variety of axes. So 3 of the most important axes that have seen some significant thought and insight from often beginning with collaborative dialogue between theorists and experimentalists to figure out how to explore in interesting directions, include broadening the range of lifetimes that can be probed, both towards shorter as well as longer lifetimes, varying the center of mass energy for which one can record and therefore potentially discover events, and also looking for events with more than one long or 2 long-lived particles. And for some illustrations, pushing forward in expanding the ranges of center of mass energies where one can detect signals of new physics is often critically tied up with the question of finding new ways to trigger on the displaced objects themselves, because those are the things that tend to be low background. That is a major challenge experimentally because, again, these objects require non-trivial reconstruction strategies. Since triggers must be done at the hardware level in many cases, it becomes very hard to find sufficiently accurate reconstruction algorithms that can be put in at the trigger level to result in an acceptable amount of data flow. However, this problem is being addressed, especially in conjunction with new detector capabilities for Run 3 and beyond, in a variety of creative ways. This plot is an example of a recent analysis from CMS, which uses data scouting, so a partial readout of the full event rather than the entire readout, which allows a extension of data recording down to center of mass energies that would otherwise be an unacceptably large rate, where they look for di-muon resonances down to rather surprisingly low values of the decaying particles mass, so down to few GeV and even a little bit below. And being able to directly access triggers on these low mass displaced objects allows this search to put qualitatively new limits on the parameter space for models that give displaced time muon resonances. Other ways to extend the center of mass energies also involve other ways to expand the ranges of lifetimes probed. You can interface with dedicated long-lived particle detectors. Phaser, for instance, helps expand coverage for light long-lived particles that are produced in meson decays by being physically situated a substantial distance away from an interaction point, and by blocking anything that is boring standard model physics, extremely exciting standard model physics to the right audience, which allows them to operate without the kinds of trigger limitations that prevent LHC main detectors from studying these kinds of objects. Other proposed detectors like Codex B and Methuselah would access larger center of mass energies, but longer baselines, again, because they're seated a further distance away from the interaction point and can run in a trigger-free operation. Of course, other clever analyses at main detectors, also LHCb, are also pushing on the lifetime front in interesting ways. And another axis, which is becoming more interesting, is studies of events that have, instead of just one or two displaced objects, which is typically predictions from perturbative theories such as various incarnations of supersymmetry, some kinds of dark matter theories, rather more complicated signatures, which are exciting, but theoretically harder to control. In particular, searches for so-called dark showers. These are events where the long-lived particles that are produced in as bound states in a confining hidden sector and are produced at potentially very large multiplicity. Something is very exciting to see is that there actually have been a couple of searches, both from CMS, for these kinds of signatures. One for emerging jets that look at the pair production of dark quarks that initiate a dark shower, together with standard model quarks that make regular jets. And very recently, a search for so-called semi-visible jets, where the pair production of dark partons ends up giving you a shower with prompt visible stuff, as well as missing energy. So understanding how to build on this set of specific model searches into a more general program is one of the sort of major program building opportunities at the current and future runs of the LHC. And one of the major discovery opportunities for new physics that looks sufficiently weird to have evaded current searches, while remaining at sufficiently interesting coupling strengths to us to be produced in appreciable quantities. And in addition, can arise naturally in many kinds of well-motivated theoretical models, although that's not the focus of this talk. So these events have come to be known as so-called dark showers. When I use the word dark showers, I mean events that have non-trivial evolution in a hidden sector, so among a group of particles that are standard model singlets and talk to each other more strongly than they do to the standard model. In particular, this often ends up with potentially quite high multiplicity final state objects, often variable multiplicity. This can arise most naturally in confining hidden sectors, although very similar phenomenology also arises when you have perturbative hidden sectors with long cascade decay chains. Of course, there are ways in which these two pictures can be secretly the same thing through dualities. These kinds of dark showers arise naturally in many models. For some recently famous examples are neutral naturalness type solutions to the hierarchy problem, where the partners to standard model particles that are responsible for curing the quadratic divergences in the Higgs mass are charged under a dark QCD rather than our QCD. Other examples come up in dark matter models of various kinds. Some of them are asymmetric dark matter, some of them are strongly coupled thermal dark matter of various kinds. In more generality, there is no particular reason why we should expect nature to give us perturbative electroweak scale physics. If nature gives us new physics that we can study anywhere near the electroweak scale, there is no particular reason why we should expect it to be perturbative. It is a generic possibility that nature may have chosen a non-perturbative hidden sector, a confining hidden sector, let me say more precisely, for us to explore. So we should, especially now that we have carefully mapped out the easier territory of searching for perturbative signals of non-confining new physics at the LHC, we should give some serious thought to thinking about searches for harder cases that are more challenging to classify theoretically. So some characteristic features of dark shower events that set them apart from more standard searches for physics beyond the standard model. So that they have.
Excuse
Yes,
me.
Please.
Dark showers are visible or invisible? Visible dark shower.
Good. So if everything in the dark shower is invisible, then it's just missing energy. So if it's going to be interesting, at least some of the particles have to be visible. I'll say more about that. Thank you.
Okay. Okay.
So they should have a variable and potentially large object multiplicity. They will have a non-standard model-like distribution of both energy. So the distribution of energy, the patterns of energy flow will look not like QCD and not like perturbative known decays of standard model species. They will have non-standard model-like distributions of flavor as well. They may make more muons than typical standard model jets. They may make more B quarks, say, than typical standard model jets. They often end up with non-isolated final state objects. And something that is very important for understanding how to think about a search program for these kinds of objects is that they have a hierarchy of lifetimes for particles in the confining hidden sector. The long lifetimes arise from a variety of reasons, all of them familiar from QCD. So, there are hierarchies of mass scales that are involved. There are small mass splittings between different particles. There are approximate global symmetries. Some very familiar examples in the standard model where you have long lifetimes, a hierarchy of lifetimes between two different states in a confining sector, also known as QCD, are provided by the charged and neutral pions. Charged pions decay through a dimension 6 operator. There's a hierarchy of scales involved here, m pi squared over the W mass. This tends to suppress the decay of the charged pion and can make it interestingly long-lived on detector timescales. On the other hand, the neutral pion decays much faster because it has an anomalous U1 symmetry that allows it to decay promptly to 2 pions. So the different dimensions involved here give rise to a hierarchy in lifetimes between charged and neutral pions. QCD provides a number of other particles with long lifetimes for a combination of these reasons. And this is generic for confining hidden sectors, that there should be a hierarchy of lifetimes between different states in the hadron spectrum. So a couple examples in the literature of some signatures that people often talk about are cases where the shower contains, for instance, a prompt species, so some species that decays back to visible standard model stuff promptly, and then some other species that are detector stable. These give signatures that are called semi-visible jets. These are jetty events. So think about QCD. So you have sort of QCD-like pencil jets, distributions of energy, but an order 1 fraction of particles are detector stable and escape the detector. A nice realization provided by these authors is a pair production of dark quarks mediated by some new vector boson, some Z prime. You can think about these as dark pions. A flavor symmetry protects the charged pions, the charge under a global flavor symmetry in the dark sector, and it lets the neutral pion decay. So you can parameterize these class of models neatly by just saying, there's some parameter, the fraction of particles that escape the detector, vary that fraction between 0 and 1, and you can sort of scroll nicely over the model space. Another example, a bit more complicated, is what happens when your jet is dominated by a single species with a detector scale lifetime. So think about a single species of pions in QCD. In QCD, as you may know, the vast majority of information in jets sort of comes promptly down to pions. And then imagine now the pion has a detector scale lifetime. And so what happens when you produce some dark quarks is you have a parton shower that happens in the dark sector, so you don't see it. And then you start seeing these dark pions decay in the detector as the shower proceeds. So the realization provided by these people, a pair production of bifundamentals that carry Teller charge, and then the dark pions decay back to the quark pairs. So in general, when you have the production of things that evolve under a confining gauge group in some hidden sector, you expect that the light hadron species will be some combination of things with a prompt lifetime, things with a lifetime that is displaced and visible on detector scales, and some that are detector stable. And that means that the signal you're looking for in your detector, when you start thinking about, in particular, things that have detector scale visible decays, is inextricably tied to the multiplicity in an event of a specific given dark hadron species, which is not so nice, because that is an infrared unsafe observable. In other words, that is not something that can be predicted with any degree of reliability in the perturbative analysis of the theory. So QCD cannot tell you from first principles how many pions you expect in a jet. If you want to predict something like that, you have to combine so you can compute a fragmentation function, but that involves some IRC unsafe information that was taken from the experiment, and then the safe questions you can ask are questions about the normalization of that fragmentation function at high energies. So if we look for these signatures with displaced objects, forced to confront the theoretical uncertainties, the incalculable theoretical uncertainties in the prediction of non-QCD-like theories where you can't take information from experiment to make predictions. So that's unfortunate. Something else that is an assumption that needs to be checked is that even the fact that we're sort of expecting tacitly our dark shower signatures to have jets is also an expectation inherited from QCD, and it is not general. QCD is an example of a gauge theory where perturbation theory works very well for making predictions for a wide range of quantities in QCD, because the 't-Hooft coupling, G squared times the number of colors, is perturbative over most of the range of energies in a parton shower. So even though we can't do things like, say, predict from the first principles the specific number of pions in a QCD jet, we can do pretty well at predicting the typical energy flow in the event, because that is dominated by physics that happens when the QCD coupling is small. The QCD coupling, of course, evolves through the course of the shower as the shower probes lower and lower energies. But the non-perturbative contributions are sort of isolated in a small range of energies close to the confinement scale, because the QCD coupling runs large, rapidly at low energies. At large 't-Hooft coupling, on the other hand, where the gauge coupling remains large over an extended range of energies, physics can be very different. At very large Hof coupling, we can use duality arguments, very famously Hoffman and Maldacena, and you expect events will be spherical rather than jetty. What happens at moderate Hof coupling? We don't know. That's in the region where both perturbative and dual descriptions break down. There have been some recent work in making some toy models to help explore this space. But these should be understood as useful toy models rather than very solid theoretical predictions. This is a regime where our tools do not work. And if we are designing searches, we need to be careful about the assumptions that we are making and understand the regions where they break down in order that we do not preclude ourselves from seeing interesting physics. Now, the fact that displaced objects are such clean signatures is what can help us do interesting physics despite these theoretical challenges in making specific predictions for the signatures of the theory. If you have something like 3 displaced objects per event, this is practically background free. There are lots of caveats to that. It depends on exactly which objects, exactly how displaced. But in general, these are very clean signatures. And because they're very clean, that means if you ask for something like 3 displaced objects per event, that means you need to make very few other cuts on the properties of that event at the analysis level, at least. That means our searches can be very inclusive, which hopefully means you can do a search that is experimentally rather simple in the sense that you only need to require a certain number of displaced objects and not make other cuts on things like the specific distribution of energy in the event or the specific relationship of those displaced objects with each other or with other objects in the event. That means that regardless of what the details are of the energy distribution of those objects or the number distribution, as long as it's more than 3, you haven't cut on those, so your search retains good sensitivity to all of those possible final states, which is what enables the search program to be feasible and interesting despite the major theoretical uncertainties. So of course, if you want to have a search program go forward, you have to have a set of models that you can use, even if those models are calculating under the lamppost. The idea that we're going to use is to use QCD-like benchmarks where we have theoretical control and try to design inclusive searches using these models, based on these models, and then down the road, check that these searches are indeed sufficiently clean and inclusive to be sensitive to a much broader range of theories, including ones we are less able to make predictions for. So in order to do that, we've defined some benchmark models. This is work I've done with Simon Maupin and my student Xu Dong. So we think about a dark shower event in 3 pieces. There's production and decay. Both of those involve coupling to the standard model, which this is the easy part. It's much easier to figure out how to couple stuff to the standard model than it is to understand the middle step, the showering and hadronization, the evolution within the confining hidden sector, which is where the unknowns of hidden sector confining dynamics become challenging. So we designed benchmarks with a primary focus on production through decays of the Higgs boson, partly because that is one of the minimal ways to produce standard model singlet physics. And for the practical reason that the standard model Higgs is relatively low mass at the LHC. The Higgs is light compared to the LHC center of mass energy, which means this is a challenging benchmark for both trigger and analysis development. So the idea is, so we're challenging the experimentalists to go ahead and see if they can find stuff in the standard model Higgs, because if they can do that, the standard model Higgs, then that means they are presumably in a good position to study and discover hidden sectors that are produced at higher center of mass energies where there's more energy available and more energetic objects for triggering in particular. Standard model Higgs does give built-in triggering fallback through V Higgs associated production, where the leptonic decays of the vector boson give an alternate trigger pathway. But we also provide alternatives, and I'm running low on time, so I won't go into them. For showering and hadronization, we are using pre-existing tools, in particular the very nice PIVIA 8 Hidden Valley module provided by Torbjörn Sjöstrand and collaborators. This models N-flavor QCD. We have chosen to work with benchmark models with N equals 1. This should not be understood as a literal attempt to describe one flavor QCD. This is a way to use the PIVIA 8 Hidden Valley module to do some nice mock-up of basically interesting signature generators that span an interesting range of signatures for search benchmark development. This model has QCD-like part-time shower evolution, so it makes jet-like events. And it has a QCD-informed hadronization model. With a very stripped-down hadron sector, it features one spin 1 meson and one spin 0 meson. If you specify more flavors, they come in flavor adjoint multiplets. The thing about PIVIA 8 Hidden Valley, which can be somewhat surprising to people who don't have a lot of experience with it, is that it does not allow you to really model goldstones. It sort of assumes that the meson masses are of order the confinement scale of the theory. This means the typical meson multiplicities predicted by the PIVIA 8 Hidden Valley are smaller than what you expect from the standard model, where the pions are parametrically lighter than the QCD confinement scale. And a lot of our benchmark model building is based on trying to toggle the visible multiplicity of decaying, displaced particles in a way to help guide search development given this tool. And the choice of decay portal now.
We are already quite a bit over
yes,
time.
We're quite late. Yes, I realize that. I'm trying to speed up. Sorry, Lorenzo. Yeah, so the choice of decay portal is what tells you what the interesting signals look like in the detector. We picked a bunch, giving you things that are hadron rich, heavy flavor rich, or more electroweak. And we also emphasize that it is not generic to have arbitrarily short lifetimes, and I cannot believe I did not put that fault. So it is actually fairly hard to get very short-lived dark hadrons once the mass starts getting sufficiently light. And the lighter you push your dark hadrons, the more longer-lived they become, such that if you are interested in designing a search for, say, more than 3 visibly decaying hadrons with a decay to glue, that starts becoming questionable in some benchmarks when the mass becomes below about 5 GeV, because you typically do not produce that many. In particular, in exotic Higgs decays, where the center of mass energy is, this is not where dark shower search makes sense. So understanding where it makes sense to even look for dark shower signatures is part of the point. And as Lorenzo points out, I am badly over time. And so let me skip to the summary conclusions. This is a really interesting time to be looking at long-lived particle searches. There's a lot of technical advance on the experimental side. On the theoretical side, we are doing some work to figure out how to develop a systematic and inclusive search strategy for confining or multi-component hidden sectors, and to build that up as a program in the upcoming runs of the LHC. And I will stop there. Thank you for your attention. Apologies for the
Thank you for the very nice talk. Well, please, maybe we can have 1 or 2 questions, quick ones. Anyone, please just open your microphone. Okay, let me just ask you something, well, just partially unrelated. So, several dark matter, light dark matter, very weakly interacting dark matter models like Freezine may predict that there is a heavy charge partner decaying into dark matter and standard model. So, and if this standard model particle is, say, a lepton, then it would be rather a sort of kink, right? So a charge track that, and then, yeah, the decay occurs somewhere, perhaps in the tracker, missing energy, and then the muon, for instance. So, are you aware of any possible strategy to trigger to see something like that, or it's just going to be, yeah, an event that is not recorded because I don't know, consider like a cosmic ray, because I mean the muon does not point to interaction point. So, do you think it would be feasible? Because that's a quite generic signature for what I understood.
Yes, absolutely. Yeah. So there are some. So in many cases, these are called disappearing track searches, because what happens when one runs the track reconstruction is one first finds the track, and then the kink part is often not reconstructed unless it's explicitly looked for. And so disappearing track searches are something that people have put quite a lot of effort into doing, despite the challenges, because they are one of the excellent ways to discover Higgs-Zenos in the scenario where charged neutral Higgs-Zenos are very closely degenerate, which is, of course, a longstanding interest. So these kinds of kink tracks are very interesting and are sort of a natural build-on to those disappearing track searches. So a lot of the technical issues of recording the data is similar. These are hard because directly triggering on the disappearing track is usually not easy, which means you're relying on the associated objects, which often limits the mass range of the searches. But this is a topic that people are interested in for sure.
Thank you very much. I see someone in the chat writing, how big is the mass of the long-lived particle? I suppose referring to your dark shower models.
Yeah. It depends what you're looking for. For high multiplicity type searches, you tend to be interested in lighter particles, just because if you're trying to make a large number of particles in, say, the decay of a Higgs boson, 125 GeV for the standard Higgs, obviously it's hard to make a lot of 30 GeV particles in the decay of the Higgs boson. You're just limited by U-gas. But of course, if your parent particle is significantly heavier, say 750 GeV, some for the BSM parent, then you could be interested in much longer, much heavier things. So it really is a model-dependent question.
Okay, thank you very much. I don't see other questions. So, well, thanks, Jesse, again, and let's move on. So last speaker of this session will be Professor Yeon-Min Lee, talking about, relaxation of the Higgs mass and cosmological implications. I see already your slides, so please go on whenever you're ready.
Okay. Thank you for your kind invitation. I'm happy to talk about recent a series of work based on these references written there. This is about the Higgs mass, new solution to the Higgs mass problem. So let me first give you an introduction, and then I will talk about four-form flux relaxation for Higgs mass problem, and then what is the application of four-form portals for cosmology, and then conclude. So although this workshop is about supersymmetry and unification, and there are also alternative solutions to the hierarchy problems. So supersymmetry based on, as you know, the superpartners, and then pion-like composite, if Higgs is the composite particle, and then if there's a classical scattering variance, that you would expect that there's the light part. I mean, the Higgs mass is given by the vacuum expectation value of light scalar, and then it's in the neutral naturalness. You might impose discrete symmetries to impose the symmetries between the standard model and the mirror sectors. And recently, it's not recent anymore, but about 60 years ago, there was an interesting proposal with the cosmological relaxation to solve the hierarchy problem without relying on any symmetry or parent symmetry. So in each of solution to the hierarchy problems, we are expecting new particles appearing not far from the electroweak scale. In the case of SUSY, as you know, superparticle masses around TeV scale, and the composite thickness, you might expect top partners or like resonances around TeV scale. And in the case of scale invariance, the light new particle, because of the approximate scale invariance, you might expect a light scala to appear. And the discrete symmetry is if mirror symmetry is exact, then you expect dark Higgs and dark QCD, etc. And the cosmological relaxation, let me focus more on this later. And you are expecting the action like relaxation particle to be expected. So, sorry. But we haven't found any evidence for particles at the registry, as shown in this list of exclusion plot, and also and the searches for other new physics. There is no convincing evidence for new particles at a few TeV or below, except that there are interesting anomalies recently reported by genome 1 ton or semi-leptonic decays of B measures or mu1G-2. Nonetheless, have we missed something, or do we need new ideas? So we need to understand particle physics problems maybe in the context of the cosmological evolution from the Big Bang, inflation toward the current universe. That there are many things going on in this cosmological evolution. So one interesting idea was to use cosmological relaxation. The point is that the physical parameters, including Higgs mass, evolve in the early universe. So for instance, if you consider action like scala for symmetry region, then there's a linear potential which is broken shift symmetry softly, then the linear potential, and because of Higgs, because the QCD anomalies, if this action-like particle coupled to gluons, then you are inducing non-perturbed correction to the action-like particle potential. Then you have oscillating pattern here. Then and then in this scalar particle coupled to Higgs, then depending on the value of this action-like scala, the Higgs mass depends on this field value. So when initially you started with the symmetry with the electroweak symmetry, then electroweak symmetry is broken as soon as the Higgs mass parameter becomes negative. And then this rolling of this new scala can be stopped because of the back reaction of the QCD non-perturbed correction. Then you can stop the rolling of the scalar field. In this case, the bottom line is that there is no new physics needed up to high scale, and optimally, the new physics scale is about 10 to the 7 GeV or so. Sorry. So the four-form flux, the ideal four-form, is not new. It started already 80s, and the four-form is just to fill the strength of the three-form gauge field, and there's the net effect of the four-form flux without coupling to any particle. Then this four-form flux, just from the equation motion, you can solve this equation motion to get the four-form flux to be this function Q times epsilon tensor, epsilon mu nu rho sigma. Then if you put this IP mu nu rho sigma back to the Lagrangian, then you will get the effective cosmological constant being proportional to this flux parameter. So we feel if you have a negative cosmological constant, I mean, in this Bayer cosmological constant, it's negative, then you can cancel this Bayer parameter to get a small or zero, vanishingly small cosmological constant. So in the case of, but the flux is quantized. So if you have, there's a limited precision to get the cosmological constant to observed value. So if you have a multiple four-form fluxes, then you can get the accurate scanning of the cosmological constant as observed. So just the flux parameter contribute to the cosmological constant by just shifted the cosmological constant. But if you couple the four-form to the three-form gauge field to the membrane, then the four-form flux can be dynamical in the sense that it changes by 1 unit by producing closed membrane, as you shown in this picture. And this the dashed line is boundary between two regions. The region outside is with the flux parameter Q, original flux parameter, and the region inside is flux parameter with the Q minus E. E is the membrane charge. So as a consequence of producing closed membrane, have a different vacuum depending on the regions. But there is because this is a quantum process, there is a probability to produce this closed membrane. That this probability depends on the membrane tension and the difference between the cosmological constant inside and outside. So delta lambda is the cosmological constant. And this is the bounce action is the approximation without including the curvature, space-time curvature. So including gravity curvature effect, and this probability is modified by the curvature. And in the end, for large curvature approximation or large radius of the membrane, closed membrane, then this probability is given by the exponential e to the minus 1 over effective cosmological constant. So of course, as far as you have non-zero flux parameter outside a closed membrane, you can inside in the region of your interest, if as far as the flux parameter is sufficiently large, you are able to produce more membranes. But the bottom line is the probability becomes smaller and smaller as the cosmological constant becomes the smallest. So then effectively, membrane production stops when the cosmological constant reaches the true value. Then this process, membrane production, stops afterwards. So what is the UV origins of four forms? And then I think we know that, for instance, in M theory, there are M2 brane or M5 branes. Those are sources for four-form fluxes. In the case of M5 brane, which if those are wrapped on 3 cycle in compactations, and then the effective the membrane tension and membrane charge given by these expressions. And in this though, I want to make this membrane tension and the membrane charge separate for my purpose for scanning of the Higgs mass. So the bottom line is that it is possible to get small membrane tension and charge if the volume of the internal space is large or small element dimensional Planck constant. And also, if supersymmetry is broken, there is no BPS like relation between tension and charge. So the small membrane charge is also technically natural. So then we can produce membranes more easily if the charges are small. And also the four-form fluxes have been used to scan the SUSY breaking scales, as discussed, for instance, this paper, because the if you spusometrized four-form, you could have non-zero F-term, and then the F-term can contribute to the SUSY breaking. And also in the case of three-form fluxes, in string theory, it is possible to stabilize moduli of compactations. So this is the landscape of four forms in my talk, but let me cover some of them, and those issues are related, and then we can solve some of them at the same time, but I'm not aiming to solve everything at once. So the physical parameters depend on four-form fluxes, so-called four-form landscape, and Higgs mass scans because of the coupling to the four-form flux, and the cosmic constant, as I said before, can be corrected because of four-form, and because of volume coupling, and the inflation. Even though the four-form doesn't have a dynamical degree of freedom, it could be dynamical once it couples to gravity non-minimally, and if it couples to some pseudo-scalar particle, then the pseudo-scalar becomes massive. So, and then this pseudo-scalar can be an inflection candidate, for instance. And then, as I said, there's a SUSY breaking, and also if there are hidden sector and the visible sector communicated by four-form, then it is possible to have four-form flux-mediated dark matter, for instance. So I spent some time on introduction. Let me go on to discuss the main theme of these talks about relaxation, four-form relaxation for Higgs mass problem. So, so in the standard model, it is possible to introduce this kind of dimensionless parameter between coupling between four-form F mu null sigma and the Higgs field. So CH is a dimensionless parameter. So, and then if you integrate out this F mu null sigma, it's like F term or D term in spusometric models, then you end up with the change in the effective cosmological constant and the Higgs mass parameter by this Q flux parameter. And also the effective Higgs quartic coupling is also shifted, but I think the phenomenologically there is no difference, just the matter of defining the bare Higgs quartic coupling. So this main changes is the effective cosmical constant and the Higgs mass. And then if you turn on one flux, then you can change CC and the Higgs mass at the same time. So this next slide, I'm showing you how to scan Higgs mass and the CC at the same time. So the bottom line is Higgs mass parameter is relaxed to a true value when the CC stops changing near zero. So initially you can start it from effective Higgs mass about Planck scale and the effective cosmical constant about Planck scale. Then you can scan. As you scan, as you change flux parameter by producing membrane, you are reducing the cosmological constant and the Higgs mass at the same time. And then the cosmological constant reaches true value, then the membrane equation stops. Then the Higgs mass determined to be a true value. Higgs mass parameters, mass parameter is determined to be true value once you choose the membrane charge about electroweak scale. Otherwise, you end up with a too large value or too small value. So we need to choose the membrane charge about that size without further fine tuning. And then in this process, the Bell parameter, Bell cosmological constant, to be tuned to get the vanishingly small cosmological constant. So this is the problem of this scenario. You need to rely on the fine tuning in the cosmological constants. Once you accept that, then it might be a solution to the hierarchy problem. So here, but in this case, in the every stage before or let's say after membrane nucleation, you are in the distal phase with a certain cosmic constant. After further nucleation of membrane, you are in another distal phase with a different cosmic constant, reduced. But your series of distal phases, and the point is that what is the maximum energy in this scenario? Because of series of these phases, the previously produced particles will be diluted. So what is important is what is the fate of the last distal phase when there is no electroweak symmetry breaking, because the effective Higgs mass equal to 0, and you have a large effective cosmic constant in the last distal phase. After last membrane nucleation, you are reaching almost 0 cosmic constant, but the electroweak symmetry is broken. And then you can infer that what is the value of the cosmic constant in the last distal phase, which is given by this expression, which is the membrane charge times critical value of the flux parameter, for which the effective Higgs mass vanishes. Then this, I think the electroweak scale square, Planck scale square. Then if this vacuum energy is converted, you can get the Hubble parameter from this vacuum energy in the last distal phase. Then the Hubble scale during the last distal phase is about 100 GeV. If this potential energy is converted completely to radiation, then you can estimate the maximum reaching temperature is about 10 to the 9 GeV. So that is the energy bound in this scenario. But in the standard model, there's I think that I'm going to talk about how to reheat the universe after series of these phases. But as I said before, in principle, we can produce particles in certain distal phase. But because of the long duration of nucleation, the previously produced particles will be diluted. And because of that, even though both Higgs mass and the cosmic constant can settle to absolute value, the universe would be empty due to this series of distal phases. Because of that, we need reheating mechanism. Also, we need because entropy problem, also density perturbation. For CMB, we need new physics, new particle in any case. But let me just briefly talk about, without introducing new particle, what is the consequence of this scenario. So because the particle mass is changing during the last membrane nucleation, because the electroweak symmetry is unbroken before the last membrane nucleation, and the electroweak symmetry is broken after. Because of that, standard model particles receive mass after the last membrane nucleation or phase transition. So you can parameterize the time-dependent mass in this form with a hyperbolic tangent, and this kappa is called the last nucleation rate. And then in the case of bosons, you can calculate the number density per mole in this form. And here, this MB is the particle mass for boson. And therefore, you can estimate what is the number density produced particles, and in terms of this effective temperature. And this, once you produce standard model particles, they will thermalize instantaneously. Then you can define the reaching temperature. So this is the plot of the reaching temperature as a function of this last nucleation rate kappa. So if kappa is larger than 10 to the minus 4, the reaching temperature will be larger than about 10 MeV. It is okay for Big Bang nucleosynthesis. And then, but in this case, as I said before, the probability for the last transition is very suppressed unless you have a small membrane tension, although I didn't discuss in detail. So naturally, I think every scale, there are Planck scale and weak scale, nothing else. Because of that, if you don't introduce intermediate scale, then the transition rate for the last nucleation will be exponentially suppressed. Because of that, this particle production mechanism might not be efficient. Because of that, we may need to introduce new physics. So if how to realize reheating, I think that one scenario is to introduce new scala trapped in the minimum of the potential, so force vacuum, and it tunnels after the membrane nucleation. And it may be realizing inflation and reheating at the same time, but I haven't worked on this in detail. And also, reheating is possible if the potential for certain scalar field depends on flux parameter, for flux. But before the last membrane nucleation, it has certain minimum, but this minimum changes because of the flux change. Because of that, you can start it from kind of misalignment after the last membrane nucleation and setting the initial condition for the rolling of the scalar field. So it's like an action-like particle, but for different region, it is possible to have misalignment so that you could have reheating. So I'm focusing on this latter scenario in my talk. So this is what is new in my work is to generalize the four-form coupling by including this minimal coupling to gravity. So initially, as I said, the four-form, if you introduce four-form flux, there's no dynamical degree freedom. But if you couple this to gravity, then you are generating extra scalar field, which is the sigma field here with a certain potential here. So once you actually this outer term is needed because of the stability of the additional scalar field. So once this psi is greater than this gravity coupling C1, then we have a stable scalar field, scalar potential. And this extra scalar may be responsible for inflation and reheating. The effective scalar potential in the Einstein frame can be written in this simple form, but there are several exponential potentials and the effective parameters in this potential. But the bottom line is that there's a minimum of the new scalar field depending on this the flux parameter. So this flux parameter Q and the lambda effective is also depends on the flux parameter. So once you reach the true minimum, lambda effective vanishes, then you only have this quadratic form of the new scalar field, which has a minimum, and we are reaching the true vacuum. So because the scalar web shift after the last membrane nucleation, we can start it started with a large initial potential energy before the last membrane nucleation. So then you can estimate the reheating temperature here from the perturbative decay of this new particle, and then it's possible to have sufficiently large reheating temperature in this scenario. So if you assume that the new scalar field coupled to the standard model by gravity only, then you can think about gravitational production of dark matter. So in the case of fermion dark matter, it is possible to produce it from the decay of this scalar particle. And then in this case, the decay rate to the fermions is chiral suppression, has a chiral suppression. So therefore, this fermion dark matter tends to be heavy. On the other end, in the case of scalar dark matter, there is no chiral suppression. So it is possible to produce them more, such that the light scalar dark matter is favored. And I think maybe I'm running out of time, but let me spend a few minutes to discuss this model too. So instead of pure gravitational coupling, we can think about new scalar field, which is a pseudo-scalar, and with a four-form coupling in this form. Then this is action-like particle. So this is the mechanism to give mass to action-like particle because of the four-form flux. And then you can get this the effective potential for phi with a minimum. And this Lagrangian has a shift symmetry because you can if you shift scalar field by constant, you can shift the flux parameter appropriate constant. In this scenario, quadratic inversion can be realized, but observationally it is ruled out already by Planck observation. So because of that, we are generalizing the four-form couplings by maintaining the shift symmetry. So this is the four-form non-minimum coupling, non-minimum coupling between four-form and gravity, and therefore we are inducing this kind of non-minimal coupling to this pseudo-scalar field here, as well as R-square term. If the coefficient of the R-square term is small, then we are not introducing new particle in the effective theory. We can just decouple the new scalar field coming from R-square, focusing on the effect of the four-form coupling to this pseudo-scalar field. Then you have a minimum coupling to pseudo-scalar field, and the potential is the same as before. But because of the modification in the effective Planck scale, it is possible to have Higgs or Star-Wilson-like information in this scenario. So this is the bound from Planck data, and the right-hand side is the potential shape in this model. There's the plateau and the large field value, and then there's the reheating period. And the prediction is consistent with the Planck data, and the tensor to scalar ratio can be observable in the future CMB experiment. And also, instead of using
Sorry,
the scalar
we
field
are a little bit over time. So
okay,
yeah.
okay, I will try to wrap up. Okay, so same pseudo-scalar field can be used for reheating, and the Lagrangian is the same, but the difference is that there's a Higgs field coupled to the four-form flux. Then you have this kind of square form of the effective potential for the pseudo-scalar field and Higgs. And in this case, also because of the mechanism of shifted vacuum expectation value, we could have started with the non-zero initial vacuum energy, and we can have a reheating temperature about 100 G scale. And then I think in this mechanism, it's natural to think about fermion dark matter, which coupled to the pseudo-scalar field. And then this pseudo-scalar field communicate between standard model and the dark sector. And because of the pseudo-scalar nature of this mediator, there's a separation in the direct detection, while there is observable signatures for indirect detection in this scenario. So let me just skip to the conclusions. I hope that I have convinced you that the four-form flux scenarios are interesting, although it doesn't have a dynamical degree of freedom. It could change the physical parameters in a meaningful way. In particular, Higgs mass and the cosmic constant can be scanned at the same time because of the creation of weak-scale membrane charges. And sufficient reheating is required in this scenario by introducing additional scalar field. And I illustrated certain scenarios where the reheating and other cosmology problems can be addressed. Thank you very much.
Thanks to you. Very nice presentation. The parallel sessions are about to start, but of course we can take a very quick question. This room will be used by the neutrino session, I think.
Sorry.
I apologize to the next chair. So, any question for our speaker? So, sorry, just a very quick one. So you mentioned that you have also the possibility of producing dark matter with the right relic abundance purely gravitational with your mechanism.
Yeah, yes.
So in that case, you don't see any possible way to test, observe this kind of dark matter candidate, or there is some hope, some option open?
So yeah, I think I consider non-thermal production of dark matter and the thermal production of dark matter. So I think that my point is that it is possible to accommodate both scenarios in this setup. And for non-thermal dark matter, I think the situation, I don't know, the methods case might be different, maybe depending on the scenarios. So in my case, the dark matter, fermionic dark matter is about TeV scale, and GeV scale is scalar dark matter. So methods case might be different, and yeah, but I don't know, how to probe that.
Okay. Thank you very much. So I think it's time to close the plenary session of this morning. Thanks to everyone who talked and attended. So, well, for the plenary, see you again at 8 p.m. Beijing time. And then I will leave the room to the neutrino session and enjoy your parallel sessions too. See you later.